Pattern recognition is the first of the 4 components of our computational thinking way of problem solving that we're looking at in this course, right? So there's the 4 components, remember? We had the abstraction, we had the decomposition, we had the algorithm, which we kind of leave to last. And the first one we're going to look at is this pattern recognition. Now, the idea in the pattern recognition, it's all right. So the first thing we do is we're decomposing, aren't we? We're taking the whole problem solving thing here and we're decomposing it into components. And one component there is pattern recognition. That's nice. Now these little graphics here, I think they're kind of useful. If you look at them, there's a bit of meaning in the graphic. So I mean, when this we see a whole which is broken down to smaller bits, and that makes it easier to solve. When we look at this, we see something that seems to be repeated. We see a repeated component. That's what we're looking for. That's a pattern. When we see something that seems to be repeated, that is an indication of a pattern. From the pattern, we can do what? We can code this so that we can call for it and do it whenever we need it. So we're going to write a little code that's going to reproduce this for us. Now, these things we'll have to do individually because they're different. But we saw this pattern. It's something that's repeated, so we can write one bit of code, then we can invoke that code whenever we need to have this. Does that make sense? So that's the idea of having a function, or we call it a subroutine, to solve problems, right? So here's some other ideas about pattern recognition. Whenever you do those little tests that they do, you'll have a test and you'll try all these problems and see how many you get right and what time. A lot of the questions that will come up will be these pattern recognition test questions. So for example, you'll see a sequence of numbers. Now the idea of looking at the sequence of numbers, it's just a bunch of numbers. No, it's not just a bunch of numbers. You're supposed to look at it and say, what is it that relates these numbers together? And if you look at it, what we usually try and do is see a progression. And you might see here, okay, well, 6, how does it relate to 2? And how does 10 relate to 6? And how does 14 relate to 10 and 18 to 14? Oh, 2 plus 4 is 6. Plus 4 is 10, we see a pattern. So straight away, we could actually write a little algorithm that would do that, right? We take X, add 4 to it, and becomes X. And so we could just have a loop, which would just add 4 to it every time we went through. That's a pattern. Now here, this one's kind of similar. We can't do addition, but, well, maybe we can do multiplication. What if we took 2 times 3? That would be 6. 6 times 3, that's 18. Oh, there we have a pattern. You know, we're just going to multiply by 3 each time. We get to the next one. And then the last one there, this is it's too easy for me looking at it because this comes up in every computing textbook ever. All right. And it's and in some math textbooks, and it's called the Fibonacci series. So there's a fellow by the name of Fibonacci. I guess he was Italian to have a name like that. But he came up with this pattern, or is able to explain this pattern, which is a Fibonacci series. And the Fibonacci series just is that you take 2 consecutive elements in the number line, yeah, whatever. And this thing is equal to those 2 added together. And then take these 2 and add them together, and this one is equal to those 2. See the pattern? Then these 2 makes that. And then these 2 makes that. Can you guess what the next one is? See, and then, yeah. And so you could look it up on Google. You can see the Fibonacci series and you'll see exactly how it goes. And there's a nice little program that you could write to do that. Here's another pattern, which is a tapestry. Now, do you remember Jacquard's Loom from lesson 1? All right, so Jacquard's Loom, this card over here, there's a card with a bunch of holes in it. The holes, little pins go through the holes, and then that determines which strings come down when it's making the cloth. And so based on that, you can get repeating patterns. The key there is people could do this, right? You could have some people sitting at home. This would be their cottage industry. This is how they make some money. You know, they could have one of these things in their house and they could do it. But it would be a lot of work and it would take a lot of time. Or you could have a little Loom thing like this and the people would do it, but the Loom would help them make it faster. And so they make more money at a less time. That's always a good idea. And also the thing is that the pattern is quite tight, right? Because it's more exact, I guess you could say, because humans are variable. That's what we like, right? You go and buy a Turkish or Iranian rug or something like that, and we can see that a human did it because there's some irregularities, and we like that, right? Because what we're paying for is we don't want the exact pattern, which could come out of a factory in China. What we want is we want the human touch, which we can see in the slight variations. But on the other hand, we could get this. All right, so here's another pattern. You see the pattern here, right? So we got a business, and we want to keep our customers honest, and we want to keep ourselves honest, and everybody knows what's going on all the time. So we have full, clear, transparent communications. One of those communications is when we sell stuff, we give them something, or we email it to them nowadays, because we're in a more modern way. Not everything is on paper. But we have something like this, which represents all the details that they need to know and that we need to know about the sale. So we have a description of the item. Sorry, that's very small and you can't see it. I can't even see it from here. Maybe I can make it a bit bigger. Yeah, so the description of the item that you're selling, the quantity, how many of them you're selling, what is the unit price? Because what we're going to do is the total is going to be the quantity multiplied by the unit price, and then we add all those up. You've seen these, right? Everybody's got one of these when you buy one. As I said, it keeps the customer honest, it keeps the business honest. And then maybe you have a opportunity down there for keeps the business honest, keeps the business employees honest. I mean, you'll go to a business place and they'll say, when you buy things, please ask for a receipt. The business owner should ask for a receipt, right? Because they don't want the the salespeople selling stuff and putting the money in the pocket, right? We want some kind of paper trail so that we know what happened to every item. Computing can help with that a lot, right? And you'll learn about that in some of the other stuff you're going to do when we do, Internet of Things and things like that. You can put a electronic sort of tracker on every item in your store so that people can't walk out with it without that registering. And yeah, you can do things like that. Computers can help a lot. But the point that I wanted to make about this is this template that makes it easy. I mean, you could have some smart people. Why not just make it quicker, right? Why not just, we scan a barcode and then this thing gets printed out. And, then the information is held in a database. It's updated on our computer. Everything is up to date. So, why do we want to do it in a backward way when we can do it in a more forward way? I guess we could say. There's some notes about it. All the details there on that. And it's very standardized. Everybody's doing that. All right, so patterns could be recognized in two ways across problems. So what we mean by that is we've got problems that come from different spheres, different realms, but the problem seems to look the same. And we're going to look at an example of that, calculating the average of somebody's speeds while they're running around a track and calculating the average of the temperature over a number of days. That would be that. Or within a given problem, there's some components of that problem where we see a repeating type of thing, whereas so we have a business and everybody needs to have a profile for the business. So how do we gather the information for everybody's profile? We've got different people. We got salespeople. We got the manager. We also need to get a profile of our customers. So we can create a profile creation module, and it's only happening in our business, but that program creation model is being used by everybody in the business. So yeah, here's our automatically notice patterns. If we see a pattern, it will be easier to come up with a solution. Yes, I think okay, here's the two different issues that I mentioned. The athlete wants to get an average of how many of their distance on the discus, and the meteorologist, which is a weather person, wants to have the average of the temperatures. So the thing that the pattern which is there is we get a lot of numbers, we get the average of those numbers. And so the way that we would do that would be the same in both cases, right? Get the total, divide by the count. And we could write a computer program to do that. And there's a little bit about that. I mean, it's just average is average. Everybody does average. We should do average as a program. If we got enough time today. I don't think we do have enough time today. Next time maybe we can do that in anyways. So here's another one. This is the one that I mentioned a minute ago. I think we don't want to have a separate profile for everybody, a profile gathering module. We use the same module for everybody. All right, so here's another example of that. Supposing you want a program that can draw shapes. Oops, went down too far. Come back up. Oh yeah, I mean, I guess I should just make this smaller so it fits on the, yeah, all right. So you want a program that can draw shapes. You could do that quite simply, just using a few different parameters, inputs. You could say, okay, so I want the length of the side. I want the, because I'm going to have this thing draw and by the angle, it will turn there. And so if I have the length of the side and the angles, I can get the shape. Because triangles, those angles will all add up to 180, right? The other shapes will add up to different angles, right? So if I have my angles add up to 180, I'm going to get a triangle. Then I could, yeah, so length of the side, angle, then the color inside. And just from those things, we could draw all of these shapes. So like the length of the side here, this is an equilateral triangle, meaning that the sides are all equal and the angles are equal. Here we'd have a 90 degrees because it's a quadrilateral. That's other ones would have different degrees and different lengths. And from that, we could get those different shapes. The point that I probably should make, and I'm showing you the notes here because I want you to see them, is that we have this concept called object-oriented programming. You could have an object which was called shape, and then the shape could have different attributes. It could be a triangle, or it could be a quadrilateral, etc. And those attributes would have some inputs in them, which would be your length of your side and your angle and your color. And just from those, you could get each one of these as it calls there a subclass. You will, before you graduate in your degree, you'll understand all about objects and classes. So keep that in your mind. It's something, if you read about it, try and understand whatever it is you're reading. I'm not going to give you a lesson on it today. We don't have enough time on that. But it's something that you should be interested in, object-oriented programming. So basically, we create objects. In this case, we could have an object which would be a shape. And then that object would have attributes of sides, and angles, and colors. And from that, we could create different subclasses of them. Here's another object that we could create, which would be a drawing object. Now, in this object, we could very simply do it with a simple module that would create circles. So I hope that you can look there and see the common circles that are having. Everything here is a circle or a part of a circle, right? This thing here is an arc, which is a part of a circle. And so if you know how to draw circles, then you could probably make a diagram like this. So what do you need to know about those circles? That would be your inputs or your parameters for a module or a class or an object, sorry, that would be able to draw this diagram for you. So, yeah, so what do you need to know? You'd need to know the diameter, which is the distance from one side of the circle to another. If you had the radius, that would be the same information because the diameter is just 2 times the radius. So you'd also need to have coordinates of where exactly is the center of the circle. Does it say that? Doesn't say that. Okay, well, I think you'd need to know where's the center of the circle so you know where to draw it. But you need to know the color of the line. You need to know the thickness of the line. You need to know fill color if there was any fill color. Now the size of the cut would be some number between 0 and 360, which would be the degrees in the arc of the circle, right? So the arc of the circle is a part, part of the circle. 360 would be the full circle. Some number less than that. I think that's what it means by the size of the cut, which would be the angle of the arc. Got this diagram here. The idea of this is you can see some decomposition, all right, and you can see that we are actually using some some different components here. We could modularize this. In other words, what I mean by that is you could have a little module which draws circles, and you could use that to make this, and also the part of the tree. So if you look at that, you can see that there's a bunch of circles that overlap each other. And so they sort of fill in on each other. Different fill colors, different positions, and maybe different sizes. You could have a module which draws rectangles. You could get the house out of that, and also the door. Have a module that draws squares. You have modules that draws lines, and you could have a module that draws a triangle. And from that, you could make this diagram just using a bunch of little shape modules. And so, for example, and as I said, you could do this with an object-oriented program. So you could have a class for rectangle, and then that class would have these attributes: the width, height, border, and fill. And so you could say, and I would also say you'd probably have something about the position, but you could go there and say, what's the width, height, border, and fill, and draw that rectangle, and draw that rectangle. And I guess our squares are also rectangles as well. And so you could use that to do that. You could do a circle, which you'd need to know the diameter, the border, yeah, and the fill. Also, I'd say the position of it as well. And then from that, you got all these circles here. And then the triangle, you want to know the length of all the border, the lines, angles, which are going to have to 180, border, film, and the rotate, you know, is where is that triangle? Because we see these are triangles as well, right? We got one big triangle there and a bunch of little triangles there. So the rotation relative to up, I suppose. Gosh, there's a lot in this lesson, right? All right. So here we have some pattern recognition. You guys might know more about this than me. This is about cooking. So two different methods for baking cakes in the picture. Can you recognize similar patterns? All right, I'm not really too sure what they mean about this, but I do see a pattern. We do need to preheat the oven. We do need to mix our ingredients, and afterwards we need to bake. This one here is we got some whisking going on, but because we have the cream is put in between them. But I hope you see a pattern there. The oven preheating happens before you do the cooking. Mixing happens before you do the cooking. I guess that's what it means. Yeah, so that's what those arrows are. Some other things could be changed around a little bit. Right. Polygons, fundamental 3D design. We talked about that. Subroutine, the idea of a subroutine is that we have something that keeps recurring. Remember the diagram with the smiley face? It's made up a lot of circles. So we could have one routine, one little program. Subroutine is a little program that's called by another program. And so that program here is called draw circle. And draw circle takes in these inputs. And then from those inputs, it draws this. Now notice the inputs change, and each of those represents a different circle here. All right, so the inputs change there. Now this one with the 50%, that would be, it called it the cut, or what I called the arc, and that gave you 50% of a circle. But we're using the same little routine, same little program to draw each one of these circles, put them together and make our larger things. So those are components. Subroutine. In Python, which you're going to learn in this course, we call them functions. And so within the next few weeks, I'll show you how to make a function in Python. So if a function in Python is going to be a subroutine, that is something where we can just name it and it will run for us and do what we want. We'll pass it some parameters and it'll work on it. So a subroutine, as it says there, those things, it's something that's going to do something for us based on some inputs that we're going to give, and we're going to call it from within a program. The working backwards thing, we already talked about that earlier in the lesson. The idea of knowing what it is that our desired goal, our desired state. When we know what our desired state is, we can understand, well, what would it look like if we were 90% to our desired state? And then how could we go from 90% to 100%? So that would be our work. And then how could we go from 80% to 90%? How could we go from 70? You get the idea? And so we could work backwards from it. Knowing what is our desired state would be the essential. Now, the idea here is computers can be pretty good with images. They actually can work with images pretty good, because with images, we can measure things. And so if you can measure the distance between the eyes, the distance between the eyes and the nose, the distance between the eyes and the ears, a computer could recognize that these are all cats, just because those distances are of the pattern, which is cats. They fall into the range of distances that work for cats, as opposed to humans. You know, with our distance between the eyes and our nose is going to be different than a cat, right? And so we could recognize that. Yes. Yeah, they would have to do. They would have to take pictures of probably many cats, and possibly many cats, you know, maybe thousands of cats. And then based on all of those measurements, they would see that there's a pattern there, which is that cats seem to be fall into this range. And they do the same with you. Actually, we have this idea of artificial intelligence where we actually train the computer. We give it a test set of data, you know, which is a bunch of data. As I said, it could be thousands of photos of cats. And then it would just measure all the things on that and say, okay, this is what a cat is. And then when we give it another picture, it could say, oh, that's a cat or it's not a cat, based on all the measurements it's done on all the other pictures. And so they do that with us as well. So that would be able to do this here. This is kind of artificial intelligence. Really, there's a lot of data set, and you run it through an algorithm program, and there's a lot of measurements. And then based on those measurements, it says these things fall within and those things don't. So it could take a picture like that, and it could say, all right, this face here, don't know what that is, but these ones here, can see it's a human face because it's got two eyes, and the two eyes are oriented this way, and they're this far apart, and there's a nose, etc. So it could recognize that those are people. So that would be recognizing. It could then be used to count people, but then it wouldn't count all of them, right? But it could count the ones within the frame, as opposed to facial recognition, which is recognizing an individual. So we have that on our phones, right? If you've got an Android, you've got lots of security options that you have. You can put in a password, a number, special code, or you can use your fingerprint, or you can use face recognition, and you can turn that on. And so it is able to see that it's your face. Well, how can it tell, right? I mean, one day I'm here, there's a lot of light. Next day it's not light. You know, it's one day I'm sunning out in the sun. You know, there's shadows. How can it tell that it's me? Well, actually, it's probably not all that hard. It takes a lot of measurements from the face. The distance between this end of my nose and that end of my nose is unique to me. I mean, you know, yours might be similar, but won't be exactly the same. And same with the distance between the middle of my eyes. The distance between the top of my nose and the bottom of my nose is different than yours. And so that's the type of thing it will measure. You know, the color of your makeup doesn't matter, right? You know, the color of the light on that day doesn't matter. The things that it's measuring are going to be unique to you. And there are going to be things that don't change, because, so for example, I'm kind of old. You know, my face is a little bit different now than it was when I was 20, but some things haven't changed. The distance between here and here hasn't changed, right? The distance between here and here hasn't changed. So those things are the things that it's going to focus on, the things that are going to be unique and that are going to stay the same over time. And so it can do that and do facial recognition. That is actually kind of a big thing. It really does happen. Now, what I mean by that is, you might say, oh, well, okay, so we got it here, but yeah, they're not really using it on me. If you're walking around in the streets of London, there's video recorder that's videoing you all the time, right? That's on the streets of London all the time. Everybody who walks out there, their photos being taken. And if you're walking on the street of any big city in China, I mean, you'd look up and you'd see the camera. I mean, look, there's a video there of me and you now. So this is just everywhere. There's all kinds of images of us, of everybody that's everywhere. Now you might say, oh, well, what do they do with that? You know, your data storage is getting cheaper and cheaper all the time, isn't it? So they can store that. They can store that, right? 10 years from now, I don't know, the FBI is looking for me for some reason. I don't know why. They probably want to give me an award or something, right? No, I'm just kidding. But, you know, somebody doesn't like you. And so, you know, they go and talk to the FBI or the CID or whatever. And they'll say, oh, yeah, I remember that Mark guy. Back in 2022, he was doing something in his class. No, I wasn't. I would say, okay, so I'll dig out the thing, right? Facial recognition. Is that Mark? Yeah, that's Mark. Get the idea? So, I mean, it's not the same world that we used to live in. It's new. Critical thinking, basic introduction. We're going to talk, we talked about this today. So we do have to talk about these other things. We will. Got a few more slides for today. What is computational thinking? Can we answer this? I don't know where these questions came from. I just got these slides today and here's these questions. But here's my guess. Maybe something like this will show up on the quiz, on the exam. I don't know. I have the quiz, but I haven't looked at it. So maybe that means it won't show up. Anyways, could you answer this? What's computational thinking? Giving instructions to a computer? Thinking like a computer in binary. Most people don't think in binary. I think sometimes we do. I like that. That's not a terrible answer. Okay, that's not a terrible answer. But binary just means, you know, true, false. Yeah, we do that sometimes, using a set of techniques and approaches to help solve problems. Yeah, and actually, it does say specifically in our notes that computational thinking is not thinking like a computer. It's a way of solving problems so that we can use a computer to help us. So that's a trick one. Yeah, we don't think like a computer. All right, so what do you need to think computationally? To help us, why? Sorry, why do we need to think? To help us to program. As I said, that's not a terrible answer. I don't think it's the right one, but I don't think it's terrible. To help us to solve complex problems more easily. I'm liking B here, right? It's not to help us think like a computer. We don't want to think like a computer. Computers think like us. That's what we want. Right? What we want to do is we want to help the computer to think like us. But first, we got to think in a methodical way. And yes, we use it to solve problems, not necessarily using a computer, but maybe we're going to use the computer to help us solve the problem that we sorted out with our computational thinking. But you can do computational thinking without a computer. You're solving the problem of your car won't start. You could do computational thinking without using a computer. You know, okay, car won't start. What does a car need to start? Car needs to have electricity, needs to have gasoline. Okay, needs to. So what am I going to look at? I'm going to look at the electrical. Then I'm going to look at the computer, because the car has a computer. Yeah, I could check that. But I'm going to check that it has gasoline. And if it doesn't, well, that would explain why it won't start. Okay, so yeah, all right. Which of the following is not a computational thinking technique? Okay, there was 4, right? Which one? Coding. Trick question, isn't it? Coding is writing computer programs. So I hope we're getting the idea there. Computational thinking is not like being like a computer. Coding is doing it like a computer, but that's not computational thinking. Which of the following is an example of thinking computationally? Planning out your route, going to meet a friend? Yeah, okay, so we had that example, and that's why you said yes, because yeah, we talked about that for like 5 minutes, right? When you're going to meet a friend, wandering around. So that's not, obviously the first one was when you go to meet a friend, asking a parent to plan your route. So computational thinking was planning, and we actually gave that example. Good answer. We got that so fast. I hadn't even finished the question, and they had the answer. Which of the following is not an example of computational thinking? Not planning to collect and where to exit to complete a video. That's kind of an example we had, right? How to beat your enemies. Yeah, good. I think the two that have the planning on how, that's computational thinking. Accidentally is not computational thinking. Good answer. Thank you. Which of the following is not an example? Another one. Bossiest friend decide where you shall go. That's an example of psychologically thinking. And psychology, they say, is a science. Considering the different options carefully before deciding upon the best one. Okay. Discussing with your friends how much time and money you have before choosing from a short list. So which one is not? Yeah, letting the boss, yes, that's not computational thinking. As I said, that's psychological thinking, right? It's like, do I still want to be friends with this person? How much is it worth? Sort of a confrontation. Yeah, I'm on confrontation mode today. So, bossy friend, go to heck, or no, I'm not in confrontation mode today. So bossy friend, yeah, you tell us where to go, whatever. What is a complex problem? Problem that at first is not easy to solve. Stand. None of those answers are terrible. So in this case, this is the one where none of the answers are terrible. You have to find the best answer, which is the one which is the least terrible, which is the most right. Which one? I mean, I kind of told you the answer there, right? If none of them are terrible, the one that says do both must be the best one, right? Problem not easy to solve, and it's not easy to understand. Which computational thinking technique involves breaking problems smaller parts? Yeah, you got that on the top of your head, right? You know that one. Good stuff. Create the successful computer program. How many computational techniques are usually required? We talked about 4. There may be some others. For sure, somebody's got a way of doing it with 5 steps, for sure. You know what I mean? This is just a model. It's a nice model. It's the model that we're using. Okay. When is a computer most likely to be used? Ooh. All right. I hear some people saying B. All right, I like that answer. That's the most likely, but you could use computers. Yeah, we're getting towards artificial intelligence, right? So, but yeah, I'm liking B there. Okay, well done, students. I think we kind of finished that. If you have any questions, I'll be here for a few minutes. Otherwise, you are free to go. Thank you. And we've run out of time.